Okay, the first page of these Castigliano sets of notes shows a page that came out of my notes that I wrote on fairly heavily in Stillwater and talked about in Tulsa. I'm going to go ahead and use this page anyway. What we're talking about here is a circular ring that covers 3/4 of a circle. In the original picture, this ring had a side load F, and that's what we're going to be paying attention to here. We also talked about the possibility of replacing the side load with a vertical load to see how it behaves, and then applying a dummy load Q to learn a deflection in another direction. But in this case, we're going to pay particular attention to this side load and calculate the sideways deflection because of this sideways loads. That means we need to write the strength of materials properties in terms of this load F, and with Castigliano we'll be taking our partial derivatives in terms of this load F. Okay, and so for this problem, and what has already been given, we will have a bending moment at this point B because of this side load, and that can maybe best be seen by saying here is our point B, the load is applied at the end of the ring here, this distance is the moment arm for bending, and that distance is an r sine of theta, and so our bending moment is Fr sine of theta. We've already looked at this closely enough, I'm not going to go into exhaustive detail, but if we're talking again about this point right here and we want to talk about the torsional effect of this load, there's a torque along this line, so the torque is the torque arm is this distance right here between these two lines. That's the distance outside the triangle, and that produces that the torque moment arm is an r times 1 minus cosine of theta times the force F would give us the torque. Now that we have our moment and our torque, we're going to plug into not the energy equations but the deflection equations. If we were going to use the energy equations, and that's what this scribbling was, we could plug in the moment and square it, and then we would take our partial derivatives. Rather than doing that, we're going to plug into the deflection equations directly. And so what we're going to do now is take our moment and take our partial of our moments with respect to F. We get an r sine of theta. Take the partial of our torques with respect to F. Get an r times 1 minus cosine of theta. And then we have two energy terms, one integral for each energy term, and we're able to cover the entire beam with one integral from 0 to an angle of 3 pi over 2. And our deflection coming from bending moments is an m times the partial of m with respect to F times r d theta over EI. A similar integral, but we have torque times the partial of torque with respect to F over Gj. In these circular problems, dx is replaced by r d theta in all of the integrals. So we'll take our m equation, place it here, our partial, place it here, our torque, place it here, the partial of the torque, place it here, and that will give us the terms that we have to integrate. Actually writing in the algebraic forms of those things, realizing that we're going to have an r sine of theta twice in here, so it'll be squared, same with the 1 minus cosine theta. Plugging in those terms, pulling out the constants, Fr cubed over EI is a constant in this term, Fr cubed over Gj is a constant in this term. We're left with a sine squared here, we're left with a 1 minus cosine of theta quantity squared here, and so we can take this 1 minus cosine squared term, perform FOIL, FOIL on it to expand it into a 3-term piece, and on this one we'll have to integrate the sine squared, on this one we'll have to integrate a constant, a cosine, and a cosine squared. Remember at the top of the page that I had included from another reference the integral of the sine squared, the integral of the cosine squared, and the integral of the cosine times the sine. The integral of the cosine squared we'll be using, the integral of the sine squared we'll be using both of those. So plugging in the definition for the sine squared is, it said x over 2, we'll place x with theta, theta over 2 minus sine of 2 theta over 4. The integral of our cosine squared is going to be theta over 2 plus the sine of 2 theta over 4. And the integral of the 2 cosine of theta is going to be 2 sine of theta. The integral of a constant will be a theta. And we now have these things to a point where all we have to do is plug in the limits of integration, do a little bit of combination in algebra, and we have in fact solved for the deflection of the beam at the point where load F is applied in the direction of load F, just by doing a little bit more algebra here. I didn't finish this one up. Okay, Now another interesting question might be, and we talked about this in class briefly, what is the outward deflection because of load F? It turns out there isn't any. Another interesting question might be, what if we place a downward load F at the end of the beam rather than this lateral load F? We could then redetermine, first of all, that would only cause bending in this structure. There'd be bending only, no torsion, and we'd have to redefine the bending moment and follow through just as we did. Then we talked about possibly putting a dummy load here simultaneously with this vertical load and using the dummy load to calculate the outward deflection of this one. We're not going to do that in this example. We'll do that in another example to follow shortly. So that ends this example. Bottom line is I will show, just sort of let you see the screen with the major math on it just in case you want to pause it and copy some of this down. That ends this video.